Okay, we're recording. So welcome everyone. We are very happy to have Matt Hogancamp and Kat Hogancamp and other Kat here to talk about the GNR conjecture and categorified projectors, a survey. Go ahead,
Matt. So thank you for the introduction and the invitation. What I want to talk about today is so this is the categorification learning seminar. So this is some stuff which is from a few years ago, but with some newer stuff kind of thrown into the mix. And so the kind of big idea, or the big sort of goal, is to understand the categories of Soergel bimodules and their centers, for example. So I don't know, fancy people understand the center of the category of Soergel bimodules in terms of character sheaves, but I would rather, I don't know, trade a crazy geometry for a crazy homological algebra. And so this is the sort of motivation. And the way I want to study Soergel bimodules and things like this is to basically the same way we study Heck algebras and the group algebra, the symmetric group, is to study these things by constructing idempotents inside them. So on the level of symmetric groups, we have young idempotents. Their Q deformations live inside Heck algebras, and really what we're interested in is in their categorified analogs in Soergel bimodules. So just a rough outline of the rest of the talk. So I want to recall a little bit from the decategorified story. I will state some of the main features of the categorification, then introduce sort of a very naive version of the flag Hilbert scheme, which is the subject of the GNR conjecture, and describe its sort of the actual conjecture. This is one manifestation of the GNR conjecture, which relates certain rings of functions on the flag Hilbert scheme with the categorified projectors. And then after that, so the thing we didn't know at the time of the original GNR conjecture was how to y-ify Soergel bimodules. So I will kind of return to the story with a little bit of y-ification at the end, and we'll see how far that takes us. Okay, so I've prepared some notes here, at least for the first part, just to kind of save on some time for the background. So to begin with, I want to remind us of just this sort of big picture of what idempotents in a symmetric group algebra look like. So first off, the primitive idempotents are parameterized by standard tableau on n boxes. The central idempotents in the symmetric group algebra are indexed by partitions. So for each partition, there's a central idempotent, and then that central idempotent decomposes yet further into a bunch of primitive idempotents according to the number of fillings of the Young diagram of that partition. So we'll denote the primitive idempotents by P sub t. We'll denote the central idempotents by E sub lambda. And the thing that I want to mention here is that if you consider sandwiches, so if you look at the symmetric group algebra with primitive projector PT on the left and PU on the right, then this whole space is one-dimensional if T and U have the same shape. So I'll use the notation SH to mean the shape of a tableau. That's just the Young diagram of which it's a filling. And so this is one-dimensional if T and U have the same shape, and zero-dimensional otherwise. So this is, you can think that these idempotents are basically responsible for the decomposition of the symmetric group algebra as a product of matrix algebras. So the whole symmetric group algebra splits as a product over all partitions. And then yet further is a sort of product or direct sum over all standard tableau which fill those partitions of these one-dimensional vector spaces. And this describes the symmetric group algebra as a product of matrix algebras. And just kind of record here, if we were interested in the center of the symmetric group algebra, then this gives us one approach. The center of a matrix algebra is just one-dimensional, generated by the scalar matrices. So sorry for being too elementary here, but the center of a product of matrix algebras is sort of one-dimensional for each block. And here what that means is, so the center of the symmetric group algebra is just free with the basis of central idempotents. There's another object we might be interested in, which is not just the center of the group algebra, but the cocenter. So I might call this the trace or the cocenter of the symmetric group algebra. This is defined to be the symmetric group algebra modulo commutators. Similar argument. So the cocenter of a matrix algebra is one-dimensional, generated by just the usual trace function. Like, sorry, it's one-dimensional generated by any of the okay. I should say dual to the trace of a matrix algebra is just the usual trace function. Okay. Anyway, so this is spanned by classes of primitive idempotents or classes of primitive idempotents. The thing to note here is that two different idempotents in the same block of this matrix algebra are equivalent modulo commutators. Okay, so this can also be spanned by primitive idempotents. For each lambda, you choose your favorite tableau with that shape, and you use primitive idempotents span. Anyway, so this is one way to see the isomorphism between the center of the symmetric group algebra and the cocenter. Okay, this is the sort of thing that we'd like to try to categorify if possible. So I will tell you that part of the story. So we're interested in categorifying this story. So I'm sorry, I'm getting ahead of myself. So that was the story for the symmetric group algebra. I should say the Hecke algebra is Q deformation of the symmetric group algebra, and the story is entirely similar to that of the symmetric group algebra. The primitive idempotents are indexed by standard tableau. Central idempotents are parameterized by Young diagrams or partitions. And you again have this. If you take your coefficient ring for this Hecke algebra to be rational functions, then again you have this semi-simplicity of the Hecke algebra. So Hecke algebra splits as a product of matrix algebra, just like in the case of the symmetric group. And we were interested in how this is this kind of structure persists or doesn't to the categorified level, roughly speaking. So me and Ben Elias constructed complex. So the Hecke algebra is categorified by the category of Soergel bimodules. I assume this is well known enough that I can get by without saying more than this. And if you want to categorify elements of the symmetric group algebra, or rather elements of the elements of the Hecke algebra, you should look for objects of the Soergel category, or maybe complexes of objects of the Soergel category. And so this is what me and Ben do. So there are certain complexes of Soergel bimodules parameterized by standard Young tableau. This notation here means the homotopy category of chain complexes, but which are bounded from the right. So they may be infinite, like they're definitely infinite, but they're bounded at least in one direction. And then the main properties of these complexes is that they're orthogonal idempotents of the homotopy. So if you tensor PT with PU for different T and U, then you get 0, or at least something which is homotopic to 0. If you tensor PT with itself, you get PT back up to homotopy. And then this statement that you have enough idempotents, that they sort of add up to the identity, is manifest on the categorified level by this identity. So you take the monoidal identity in the Soergel category, that's the identity bimodule. Well, this, you think of this as being a complex in degrees, just supported in degree 0. As a complex, it is homotopy equivalent to some elaborate arrangement of these guys PT. You take the direct sum of all the PTs, but you turn on some sort of, each PT has some differential internal to it, but you don't want to just take the naive direct sum. You want to take the naive direct sum and then turn on an extra part of the differential, which is strictly triangular with respect to some natural order on Tableau. And this direct sum with that extra little differential is collapses down to the identity bimodule. So we'll see an example of this on the next little page. But with this construction, we can now state a couple of problems. The first one, I admit, is not it's a vague problem, and it's probably extremely hard, but I'll state it anyway. The first problem is, to what extent can we understand how this whole homotopy category is built up out of these sort of categories here? On the decategorified level, we know that if you take a sandwich, the Heck algebra sandwich between a pair of primitive idempotents, then that is one-dimensional. But in the categorified level, this is potentially some very interesting category which sort of categorifies a one-dimensional vector space, but is not in itself entirely trivial. One of the reasons why it's not entirely trivial is because these projectors can have endomorphisms. So one of the basic problems is to understand the endomorphism rings of these projectors. Okay, so this is like the basic problem that we like to understand. As it turns out, these things actually have a lot of structure, even if we don't yet have a good way of getting a hold on this problem in general, but these endomorphism rings do actually have a lot of structure, and then and later we'll see that these are the subject of the GNR conjecture, or at least one component of the GNR conjecture. Okay, so my favorite example. So when n is 2, we have 2 standard tableau. We have 2 Young diagrams and then a unique fill-in for each Young diagram. So let me describe for you the 2 projectors in this case, and then how we'll do everything. I'll describe for you how the identity can be written using the 2 projectors, and we'll also describe their endomorphisms. Okay. I want you guys to feel the sort of same surprise that we all felt, 4 years ago or 5 years ago or 6 years ago, whatever, when we realized that these computations in the world of Soergel bimodules were exactly matching computations in the world of Hilbert schemes. So in order to appreciate that, you have to kind of see some computations. So I'm sorry if you're not that kind of person, but I am, and computations I think are really useful. Okay. So for the Heck algebra on 2 strands, we have the following basic setup. So start with, we have the polynomial ring with 2 variables. We think of this as being so the symmetric group on two elements is generated by just a single reflection. This acts on the polynomial ring by swapping. We'll be talking about bimodules over this polynomial ring, which means we will be considering sort of the algebra R tensor R. Just for the sake of notation, I will identify R tensor R with this polynomial ring in 4 variables. So here we have the left, these guys represent the left action of x1 and x2. These guys represent the right action of x1 and x2. Next, we have this special Soergel bimodule, which is the quotient of R tensor R, where we identify symmetric polynomials on the left with symmetric polynomials on the right. So explicitly what that means is x1 plus x2 gets identified with x1 prime plus x2 prime, and x1, x2 gets identified with x1 prime, x2 prime. As a little exercise for, I don't know, any grad students who are in the audience who like don't know, who haven't done computations with Soergel bimodules yet, it's very useful. I mean, you can maybe even do it in your heads, but show that the ideal generated by, well, show that the ideal generated by these two elements coincides with the ideal generated by these two elements. That is to say, x2 minus x2 prime times x1 minus x2 prime acts by 0 on B. So that element is 0 mod these relations and vice versa. Anyway, so this allows us to build, so this relation being, this guy being 0 is what allows us to build the following complexes. So I'll consider the first complex, this projector with associated to the 1 row partition. So you start with a copy of R and then a bunch of B's. This map from B to R is just the natural projection that sends sends x1 to x1, x1 prime also to x1, and similarly for x2s. So it identifies x1. It kills x1 minus x1 prime and x2 minus x2 prime. And so that so anyway, that implies that this composition of differentials is 0. x2 minus x2 prime, if you follow it with this projection, becomes 0. x1 minus x2 prime followed by x2 minus x2 prime is 0 when acting on B. And so d squared is 0 here, and so on. Okay, so this is really a Gent complex, and I'm going to define that to be P associated to this tableau. His complement will be defined to be the sort of tail of this projector. So you chop off the head and you shift everything right. So now he's in degree 0, and you keep the same differentials. So I won't necessarily prove the fact that these are, I won't really, I'll ask you to take it on faith that these are orthogonal in the sense that if you tensor them together, you get something contractible. The basic idea is to show that the first complex really kills B. And because the second complex is nothing but B's, that'll imply that these two are orthogonal as well. So that's the orthogonality property, which I'm going to skip over the details. But the more interesting property is the completeness, or the one that's more relevant for us right now is completeness. The fact that the identity bimodule can be expressed using these two complexes. So here I have a complex which is built up. The top row is a copy of the first projector. The bottom row is a copy of the second projector. And I have, in solid purple, I have the differentials internal to each one of those guys. But I add a new term of I add a new component to the differential, which is a bunch of identity maps relating the top row and the bottom row. So this arrangement of bimodules and maps, this chain complex, collapses down to just the identity bimodule. These B's cancel in pairs, and you get just the identity bimodule. So that's the sort of statement. That's the relationship between R and the projector and the two projectors. Okay, are there any questions?
You should ignore the long chats, by the way, Matt.
Okay, cool. I didn't even notice. That's a lot. Very active. Okay, so let me, what do I want to do? How do I want to zoom? Okay, let me try not to overwhelm you with what's on this page. But here's an idea of how to see the endomorphism ring of this projector. So what I'll do is I will just construct. So here is an example of a chain map from this projector to itself. It's a chain map of degree -2. It shifts everything to left by 2 units. So it has cohomological degree -2. And here it is in terms of components. So R maps to B using via the sort of only map that makes sense. And then B is mapped to other B's by just the identities. So the existence of this chain map is representing some sort of periodicity in the construction of this guy. But anyway, here it is. It really is a chain map. So you need to check that each sort of parallelogram commutes. And then there's one more check, which is that this composition should be 0, which it is, again, because of the same relation over and over again. X1 minus X2 prime times X2 minus X2 prime is 0. So this U is really a chain map. It turns out that this actually generates all of the endomorphism ring. There are some relations, though, that I want to point out. So this guy right here is a homotopy, which, so these notes will be available later, so I don't need to go through all the details here. But this guy here is a homotopy that says X1 minus X2 prime is homotopic to 0. X2 minus X2 prime is homotopic to 0, and that difference is the same as the difference between X1 and X1 prime. And so that guy is also homotopic to 0. This next homotopy tells us that X1 minus X2 prime is null homotopic. And so this is by no means a proof, but it's the reality is that the endomorphism ring is in fact generated by X1 by U with relations generated by these two guys. So you have X1 prime has been identified with X1, X2 prime has been identified with X2. You have this periodicity map of cohomological degree -2, and then just a single relation on top of that, which is that X1 minus X2 is homotopic to 0. Just for completeness, let me just tell you the other projector and how to compute its endomorphism ring. Okay. Whereas the other complex has a periodicity map of negative cohomological degree, this one will have a periodicity map of positive cohomological degree, given by this diagram. And once again, we have essentially the same relations as before. X2 minus X2 prime is homotopic to 0. And it's not actually true anymore that X1 minus X2 prime is homotopic to 0 on the nose, but rather X1 minus X2 prime is annihilated by V, this periodicity map. And so the endomorphism ring of this guy looks kind of similar, but this relation is slightly different. So my next goal is to describe the flag Hilbert scheme and a procedure for defining algebras associated to arbitrary tableau. And the conjecture will be that those algebras constructed from the flag Hilbert scheme will be isomorphic to endomorphism rings of projectors. Okay.
Question. So in this case, can you prove that these two guys generate the center? Just on two strands.
What do you mean by generate?
I mean, a triangulated category, whatever. Like you take all the cones and all the shifts and.
I mean, they're infinite complexes. So, okay. So using
you can take the cone over the periodicity map to get a finite complex.
Yeah, you can get the full twist as a cone, right?
Yeah.
The shifts.
The answer is it generates the center for A1.
Yeah.
How
do you know? How do you know that there is nothing else like but these guys and the full twist, for example?
You mean directly or by citing someone?
By citing someone is fine.
The short answer is I don't. I wouldn't know how to prove this without using what other people. I mean, like, I wouldn't know how to prove this without asking you or Ben.
But like you guys are saying that like character shifts tell you that that's all, or
that's basically it. The problem is that all the literature on the category of sheaves is about abelian categories and not about a homotopy category. So it's a slightly different, anyway, it's tricky.
Okay, anyway, but like the expectation is that just these two guys generate this as a like triangulated category.
I mean, you only need one to get everything identity. Of course. Yeah, good question. Sorry, I don't have a great answer.
And Matt, there's a good question from Emmanuel Wagner in the chat.
Yeah.
How unique is the X that you take the cone of to get the identity when you're mapping between projectors? How unique is the lower triangular differential?
In the case n is 2 or in general?
In general, do we have any knowledge about how unique that would be?
That's a really great question. So this is not the sort of thing that you would find written down anywhere, but I believe the map between two adjacent projectors is unique up to homotopy, but adjacent in the partial order, like, yeah. So one thing that I can say though is that any two such decompositions of identity, so these are really like semi-orthogonal decompositions. So like there's a partial order on the set of tableau, and Homs between projectors only points in one direction with respect to that partial order. So any homotopy equivalence between, if you have two different expressions, like, yeah, so forgive the sloppiness. If you have two different expressions that of this form, say two different collections of projectors PT and two different decompositions of identity like so, well, the homotopy equivalence between these guys can be assumed to be sort of also lower triangular, weakly lower triangular in this partial order. And so I think that tells you that it at least intertwines the sort of adjacent maps between adjacent projectors.
Thanks.
Yep, great question.
Okay, may try in the question. So these two generate, in fact, the whole category of Soergel bimodule, of homotopy category of Soergel bimodules, right?
No. You need a twist. You need a twist of the projector. The other.
Just a moment. Don't you you can present identity as they're complex, which
Yeah, but
means
you can get B. You get 2 copies of B.
You can't get the single crossing, I would say, but you can get the full twist, but you can't.
I'm sorry, Matt, isn't that a cone of these two projectors? Oh, sorry, I'm wrong.
No. Yes, that's a great point, but it's not. It's sadly not true. So this projector here has an evil twin, in which you swap the order of the two maps. And you need him as well.
Okay, sorry.
Put an upper script evil there so that we know.
I'll just write an S for twist. Okay. Yes. So yeah. All right.
But would you expect that in general you have like enough evil twins which would generate the whole category? Like you put, like you explained it, you put projectors on both sides and you put some stuff in the middle. So can you expect that you have, okay, just this projector maybe on one side and just some braid in the middle or something like this?
Well, okay. These are great questions, but I have to think about them. Maybe let's save them for the end of the discussion. The end of it. Yeah. Sorry. The problem is I also want to y-ify things, and then you're not allowed. I'm a little bit skeptical about it. I guess maybe my one answer I want to give is that I'm a little bit skeptical that you can get everything just from. I mean, there's a tautological statement which is true. Sorry. Let me think about that later. Okay. Okay, so I would like to give. I am very much not an algebraic geometer, so I would like to give a very naive description of Hilbert schemes of points in C2, and the flag Hilbert scheme of points in C2. And luckily Eugene is here, so he can keep me honest if I say anything too offensive. We won't need very much. I just want to kind of motivate the definition of some algebras here in a second. Okay. So the Hilbert scheme of endpoints in C2 parameterizes ideals in the polynomial ring of two variables of codimension n. Okay, the flag Hilbert scheme of, I don't know, endpoints in C2 parameterizes flags of ideals. So, and then of successive codimension 1. So you choose n ideals of codimension. So each one is codimension 1 inside the next. Or previous. Okay. So the basic idea that I would like to kind of describe here is, so each partition, so in the symmetric algebra, we have the special role played by partitions in standard tableau. So a partition determines a central idempotent, the tableau determines a primitive idempotent. So I want to explain the role of partitions in tableau here in this Hilbert scheme picture. So each partition determines a subset of Hilb n in this way. So each Young diagram, maybe it's best to sort of say things this way. So I want to consider the quadrant. I'm going to, in which my Young diagrams are going to live. I'm going to do something slightly offensive, which is I'm going to call this the y-axis. I'm going to call this the x-axis. Sorry, guys. This is this is so I can match the Soergel conventions from earlier. So I'm going to fill out this whole thing with monomials. So on the top row, I have 1, y, y squared, y cubed, and so on. And the next row, I have x, xy, xy squared, and so on. You know, x squared y and x squared y squared, and so on. And the way you get from a partition to a collection of ideals is, so your partition, you draw it as a Young diagram. And then the idea is that you look at those ideals for which these monomials span the quotient. So a partition, a Young diagram determines a collection of a subset of the Hilbert scheme. And that subset consists of those ideals for which these monomials span the quotient. So you know the quotient is going to be n-dimensional, and you insist that these monomials actually span the quotient. So that defines for you an open subset of the Hilbert scheme of points in C2. And maybe you could have guessed this, but because the flag Hilbert scheme consists of flags of ideals, instead of considering like partitions determining an open set, we're going to consider flags of partitions. Well, a flag of partitions is just a standard tableau. So this statement is here. So each standard tableau on n boxes determines an open subset. Well, it determines a subset anyway of the flag Hilbert scheme as follows. So each tableau determines not just a set of monomials, but really an ordered set of monomials. So for example, if our tableau was, let's say 1, 2, 3, 4, 5, our ordered list of monomials here would be 1, y, x, xy, and xy squared. And the condition we enforce on elements of this set is that the first k of these monomials should span the kth subquotient, or the kth quotient. Okay, so in this way, a tableau determines a collection of flags of ideals, which is a subset of the flag Hilbert scheme. We'll see more examples here later in just a second. But the conjecture that I want to say here is that the following. So this is a conjecture you find in the original GNR paper. The ring of functions on this particular set, on the subset, turns out that it's open. Ring of functions on this subset almost compute the endomorphism ring of the projector T. They don't quite do so because you have to kill more, so you have to restrict yourself not even further from the flag Hilbert scheme to that subset of the flag Hilbert scheme on which y acts nilpotently on the quotient. Anyway, so this kind of somewhat abstract thing, this ring of functions on the flag Hilbert scheme is supposed to be isomorphic to the endomorphism ring of this projector PT. I'd like to give a more concrete description of these endomorphism rings, these coordinate rings.
I think pedantically one need to complete both sides sometimes. So we don't know if it's true without completion. There are some.
Yeah. So
like for one row and one column, there are no issues, but like for very general T, you might need to complete both sides and make sure that the completions are isomorphic.
Right. So you might need to restrict this further to like a formal neighborhood of T or something.
Yeah, something like that. I mean, you choose like one particular open subset, but like, I mean, you have to explain like why this is good open subset. And maybe one more remark. So the Hilbert scheme is actually a smooth algebraic variety. And so if you take an open subset containing one point and you complete at that point, that's like formal neighborhood. So you know what's going on. Flag Hilbert scheme is very much not smooth. And so there are lots of issues there. And that's another thing.
Yes, there are lots of
very careful.
So there are lots of issues that I have no interest in. The flag Hilbert scheme is a really kind of I don't know, not very well behaved object. And certainly the way I've defined it isn't sufficient to address those issues. But it will motivate the definition of some rings, and then those rings are going to be some stuff that we can compare with Soergel bimodules. Okay, so to describe these rings, we need something a little bit more concrete to describe our elements of the Flag-Hilbert scheme. So an element of the Flag-Hilbert scheme is a sequence, it's a flag of ideals. What I'm going to do is I'm going to choose an identification. So C of xy mod, the first ideal is one-dimensional. I'll choose an identification. I'll choose a base, an element of that, which I'll identify it with C. Polynomial ring mod I2 is two-dimensional. So I have already my basis element in C1. And anyway, so sorry, I'm not saying this well, but I want to choose identifications like this in general. Basically, my flag of ideals, if I look at the quotients, I'll identify them with standard coordinate subspaces inside Cn. After this identification, the polynomials x and y act on these subquotients. With respect to the bases we've chosen, so i's are ideals, so they're preserved by the action of x and y, which means that x and y preserve this sort of natural filtration by coordinate subspaces, so they act in a lower triangular way. Okay, so our element of the Flag-Hilbert scheme, after making some choices, allows us to represent x and y. So we identify the subquotients with coordinate subspaces in Cm. And this allows us to identify x and y with actual matrices, actual lower triangular matrices, because they respect this filtration. And we can describe the Flag-Hilbert scheme. Again, this is very kind of a naive description, a little bit too naive, but here it is. So the Flag-Hilbert scheme is, roughly speaking, I'll say it this way: the set of pairs of matrices, n by n matrices, which are lower triangular, and with the property that if you start with E1 and successively apply powers of x and y, you span all of Cn. Writing x and y as actual matrices requires a choice of basis, and so you mod out by filtered changes of basis, which fix the vector E1. Okay. And so with this description of F tilde n, we get the following description of the subset determined by our tableau T. So F tilde n sub T consists of pairs of matrices with the same properties, but together with, if you look at the boxes in your Young diagram, so for each k, you look at the sort of monomials which are covered by boxes 1 up to k, and the span of those, they better be the same as the sort of kth coordinate subspace of C. So for example, if this is your tableau, that tableau determines a list of monomials, and then the requirement is these monomials acting on E1 span the various coordinate subspaces. So span of E1 is span of E1. This first condition is always vacuous. Span of E1 and y-E1 is the same as the C2, the coordinate subspace C2, and so on. So after a little bit of, there's still some freedom to change basis here. And so after wiggling a little bit, you can require that, in fact, sorry. So y evaluated on E1 is some, so E2 with some non-zero coefficient. We may as well by changing basis, we may as well make that a 1. So y of e1 is e2 plus some number times plus some multiple of e1, and so on. X times e1 is e3 plus something in the subspace c2. And then xy evaluated on e1 is our fourth basis vector plus something in the previous. But notice that y times e1 is something that we see earlier in our list. Y times e1 is e2 plus something in plus some multiple of e1. So this last line could actually be replaced with, I mean, this is, I'm being really imprecise here, but you can replace this condition with x times e2 is e4 plus some multiple of e2 and e3. Because x is lower triangular, you're not going to see any multiples of e1 here. Okay. And so the coordinate ring consists of, or at least the sort of algebra that we're going to obtain, which is sort of maybe inspired from this construction, is the following. So the algebra that we want to consider here is the algebra which is, it's the commutative algebra formally generated by entries of the matrix X and Y. We impose conditions on X and Y. So this equation, y e1 is e2 plus some other stuff, amounts to, well, that tells us what the first column of y should be. First column of y is e2 plus some multiple times e1. This equation tells us the first column of x is e3 plus some other stuff, lower stuff. This equation tells us that the second column of x is e4 plus some lower stuff. And so the algebra we take is the algebra generated by entries of these matrices. The relation we take is the relation that these matrices commute. And then the GNR conjecture in this instance is that algebra, if you kill y, the diagonal entries of y, you want to force y's to be nilpotent. So that's achieved by killing the diagonal entries of y. This algebra mod y's is the endomorphism in the predictor, which seems totally insane. Why should that be true? Let's do another couple of examples. Oh, and by the way, so here, this is supposed to be true as graded algebras, as doubly graded algebras. So let me talk about the gradings. So each tableau determines, so I assign weight q to the element x and weight t to the element y. That choice of weights together with our tableau determines a choice of basically by grading of the basis elements. So you place E1 in degree 0, 0. So he has weight 1. E2 was supposed to be like y times E1. So I'm going to assign him weight t. E3 was supposed to be like x times E1. So I'm going to assign him weight q. And then E4 was supposed to be xy times E1. So I have to assign him weight t. And then the weights that we assign the entries of x and y are determined by homogeneity of this equation. So x times the basis element ei is supposed to be this linear combination of basis elements ej, and the left-hand side has weight q times whatever is the weight of the I. So requiring this equation to be each element in this sum to have weight, and requiring the sum to be homogeneous forces this. Okay. So can I ask, when did I start at 5 after?
You can go to the end of the hour.
Okay. So Are there any questions?
Maybe I just want to add that the diagonal entries of X matrix are xi, which we've seen like in Soergel.
Yeah, right. So I should add.
I mean, you can edit an example.
Yes.
Like here.
So the next example I want to consider is your tableau is just 1, 2, 3. The associated list of monomials is 1y squared. And the equations we impose are, so we want y times e1 to be e2 plus something lower. We want y squared times e1 to be e3 plus something lower. But wait, y squared e1 is the same thing as y times y e1. So this whole relation can be replaced with a single relation, that y e2 is e3 plus some earlier stuff. Okay, so this tells you that the entries of y, the first column looks like this, the second column looks like this. X, there's no conditions on the entries of x. And the relation that these two guys commute forces a number of relations. For example, one of the relations is y11 minus y22 times x21 equals x11 minus x22, things like this. The weight, I should just say real quickly, the weight of x's is q, the weight of y's is t, and so that forces the weight of x21 to be q over t. And this algebra, the actions of the diagonal entries of the X matrix are supposed to be exactly the action of R on the predictors. Sorry. I think we'll see it better in this example. So here are the guys when n is 2. So for this tableau, we have a single condition on the Y matrix, and the condition that these matrices commute gives us this algebra, which when you kill Y's, ends up being isomorphic to the endomorphism ring that we saw already. So the relation that these matrices commute gives us the following relation on X's and Y's. When you kill the diagonal entries of the Y matrix, that kills the left-hand side of this relation, and so end up with this algebra, which is exactly the endomorphism ring we saw for this predictor, where I've even started writing x11 as just x1 and x22 as just x2. Okay, and then similarly, this algebra associated to the one column tableau is entirely sort of analogous to this computation. But now if you kill Y's, if you kill the diagonal entries of the Y matrix, your relation looks different. So you kill the right-hand side of this relation, and that gives you, so if you rewrite, if you call y21, you denote that by v, then this whole algebra is just polynomials in x1, x2. Sorry, you've killed y1 and y2. On this relation, which is exactly the endomorphism that we saw in our example. Okay, so I don't have much time to say anything more than this, but let me just sort of as a teaser say a question that everyone should be asking at this point. Why did we have to kill diagonal entries of Y? We took such a pretty ring and we did something silly to it. So why did we have to kill the diagonal entries of y? Can these guys be sort of restored? And so the answer is basically you don't have to kill y's, but you have to replace. So the trade-off is, sorry, I'm not saying this one. So if you want to bring these diagonal y's into the picture, there's this y-ified Soergel category defined by me and Eugene. So you take the equation d squared equals 0 and you deform it to the equation. So you introduce deformation parameters y1 to yn. You deform this equation to the equation d squared equals this guy. And given a complex of Soergel bimodules, a y-ification of that complex is a deformation of the differential that satisfies this new relation. And then the sort of y-ified version of the GNR conjecture in this manifestation would be the coordinate ring of one of these open up to completion of one of these open sets is really isomorphic to the endomorphism algebra inside the y-ified category. The y-ified category is it's a DG category if you want to think of it that way, but it also has mapping cones and homological shifts and so on. So it has a homotypic category. That homotypic category is triangulated and so on. So inside that homotypic category, so I'll write tilde for sort of y-ified complex. Anyway, so the conjecture is that the endomorphism rings of these projectors inside the y-ified category should coincide with the sort of full coordinate algebra without killing lines.
I think conjecture number 0 is that PT tilde exists, so you can y-ifi projectors.
Oh, I think I can prove that. But yeah, conjecture 0 can lift PT from the category of complexes of Soergel bimodules to something in the y-ified category. In such a way that this endomorphism ring or some completion thereof is this endomorphism algebra. So I'll stop there, but I can do either now in the question session or save this for next week, an example where I y-ify the two projectors that we've already seen and show you how this sort of, how the y's get restored in the right way. So anyway, I'll stop there. Thank you guys.
Great, thank you, Matt. And now questions.
So maybe I'll have one more pedantic correction. So in general, this is not a complete intersection. So you have these variables xij and yij. And so you have a bunch of equations which say the two matrices commute. So in general, like the equations are pretty nasty. And so I think like the correct statement would be that you take the DG algebra, which is like Kazul complex for these equations. And so in reasonable cases, these equations give you something reasonable, and this is a complete intersection. Homology of Kazul complex is just in degree 0. But in general, it's not. And like what we really conjecture is that you have this Kazul complex for these specific variables and these specific equations. And then as a, I guess, DG algebra, it is isomorphic to DG algebra of endomorphisms of the projector. So I think that would be more honest statement. But like this is again this issue that like Hilbert scheme is not smooth and it doesn't have expected dimension, and it's like really weird. And so if you just take the quotient, you lose a lot of information, and so it's not the full homology of the Kazul complex.
Right.
But
So
maybe that's too technical.
I guess I wanted to. Yeah. So that was a slight lie, but thank you for correcting that.
Eugene, you just said an isomorphism of, did I hear you right, DG algebras or just DG algebras?
Just DG algebras. No, I mean, Kazul complex is a DG algebra, right?
Yes. I just heard something I didn't know you said.
No, it's, yeah.
Matt, may I ask you a question?
Yes.
So when you compute homes between projectors, can you reduce it to computing homology of a closed braid?
Well, yeah, so sort of. So you want to compute the endomorphism ring of a projector, or?
Whichever. Are there cases when you cannot reduce it to closure of a single braid? I mean, the limit of the closure.
Yeah.
So when you say projectors, I imagine infinite twists. So when you compute homes between infinite twists, it becomes a little bit technical, because you have to know which of these infinite twists over which you can take the limit.
Yeah.
Or the order of limits matter. So I assume somehow that you have the right formulation, that whenever you have to compute home between two projectors, you can present it as the limit of the homology of a particular closed braid over the number of twists that sit somewhere inside it.
So yeah, I think that conjecture, maybe this is something that I'll mention next time, but so the short answer is it's complicated. But the relevant conjecture would be something like this. So first off, there's a big algebra to construct, which is you take the full twist on 2 strands, the full twist on 3 strands, the full twist on 4 strands, and you take arbitrary powers of these lines. So full twist on 2 strands to some positive power, full twist on 3 strands to some positive power, and so on. And you take the direct sum over all indices here. This forms some big object. You compute Homs. So maybe.
I'm sorry, the one you wrote here is your central projector, right?
I haven't written a projector yet.
Sorry.
So this is some big algebra.
Yeah. But my point is, sorry, my point is that you can reduce the homes that you compute to the computation of this home, where the left one is identity.
I know I understand your question, but I think I have 2 things I want to say. That if you want to compute Homs and like an endomorphism ring of a projector using braids, I think this is probably the smartest way to go about doing it. So each tableau determines a sequence of partitions. Each partition determines an eigenmap in the sense of me and Ben. And roughly speaking, you should take this big algebra and you should invert those eigenvalues. And that should be the endomorphism. Maybe up to some completion, that should be your endomorphism ring with the projector. So this is kind of a modern way of viewing one of these conjectures, which I didn't have time for today. But
My question was a bit different. Maybe I was wrong. So if you want to compute it.
No, I think it's the same thing, because in order to have a limit of grades, you need a directed system of grades.
Ah, yes.
And I'm telling you, the directed system is the directed system involving these eigenvalues.
Yeah, okay. But this is how you would compute it.
Yes. So your tableau determines a sequence of Young diagrams. Your Young diagrams tell you basically a directed system. It's not going to be full twists, but it's going to be powers of full twists. Of different sizes. And its limit should be the endomorphism ring.
So then may do some advertising of what we did with Alexei in relation to this.
Sure.
So you see, so in the construction that we use, a braid turns into a complex of sheaves, roughly speaking, over the double flag Hilbert scheme, roughly speaking. But we're using category of matrix factorizations, which is a smooth version of double flag Hilbert scheme. And when you close the braid, that is setting both flags equal to each other. So the closure of the braid would be computing homology over a flag Hilbert scheme, roughly speaking. So the braid that you need to compute the home between two projectors would be the product, roughly speaking, the product of infinite twists, which means that on that flag Hilbert scheme, you're isolating a particular neighborhood. So for example, if you wanted to work with ON, with bundles ON over P1, that's the only example I understand, then as your N grows, this amounts to your desire of removing the south pole. So the homology of ON and the limit N going to infinity amounts to removing south pole from P1. So the same should happen here. So when you compute this limit, you cut out this neighborhood that Eugene described to me many, many years ago from that flag Hilbert scheme. So I think if one works hard, Alexei is not here, unfortunately. Maybe we did it already. Again, I don't know. So if one works a little bit hard on our construction, this should come out naturally. When you do the limit, this cuts a piece of flag Hilbert scheme. And that's the story.
Can I add some context? Sorry. So, I mean, just two things. So first of all, like this big algebra that Matt was writing, so you can interpret this big algebra in terms of flag Hilbert scheme as well. So this.
I'm sorry, could you say it again?
Sorry, so this big algebra, so this full twist correspond to some line bundles on the Hilbert scheme, and we're computing sections, and you are computing the same sections of the same line bundles on the flag Hilbert scheme.
Yes.
And now, so these alphas that Matt was writing, so you can think of them as maps from identity to the full twist. You can think of these as sections of some line bundles. And so what roughly is going on is that you have this weird algebraic variety with a bunch of line bundles, and then you have a bunch of sections of these line bundles, and you want to look at the locus where all these sections are non-zero. So algebraically, this means that you kind of localize the algebra functions in these alphas. And that's exactly somehow what this whole machinery does for you. But on the other hand, like you can take directed system when you take the limit of this kind of powers of the same line bundle, where the directed, like this different powers are connected by the section. And this is exactly the same thing, and this is kind of easy to see. But I think the big remaining question, which is not answered, which I'd love for someone to answer, is that to identify explicitly these sections with the eigenmaps that Ben and Matt construct. And I mean, that should be doable, but it's not done as far as I know. But that's kind of the scheme. And I don't know if Matt will talk about this next time.
I might. Yeah. So, yeah. So I just wanted to say this while Eugene was writing. So, algebras of this form. So there's formally inverting one of these alphas is up to completion equivalent to taking the limit of some directed system. So that's all I wanted to say. I mean, so you allow yourself formal ratios where the numerator is a map into some product of full twists, and the denominator is some product of eigenmaps. You require these ratios to be balanced, so you need the same number of eigenmaps on the denominator as you have full twists in the numerator. And for these formal expressions, form an algebra, and that should be the endomorphisming of this. Of this guy. So your tableau determines a sequence of eigenmaps, and you take this. That would be my. That's the way of reinterpreting, I think. Something that I learned from Eugene about Flagler schemes.
Yeah, I mean, it's kind of explained in GNR, I would say.
Yeah.
Maybe I add, sorry, so on pedantic comments, so let me add one more. So you've talked about the center, and somehow I think it's very important to distinguish endomorphism of a central object and central endomorphisms of a central object.
Yes. And
there are less central endomorphisms in general. So I mean, even for these guys, for the antisymmetric, you have more endomorphisms than you want.
Mm-hmm.
And so I think like the statement would be that like all endomorphisms are given by this kind of thing. And if you want to look at central endomorphisms, you roughly speaking symmetrize, but more precisely, you just take the local ring on the Hilbert scheme rather than flag Hilbert scheme.
Yes.
And that actually should behave nicer than like, so you don't have all this kind of non-complete intersection issues and all the stuff. So like, for example, if you have y-ified, yeah, so the statement should be, if you have a y-ified projector and you look at only central endomorphisms, that should be a nice, just free polynomial algebra in 2n generators. Then you know the degrees and you know everything. But yeah, that would be great to understand.
Mm-hmm. Yeah, I definitely haven't talked very much about central things. We understand them quite a bit less than the primitive ones.
Okay, I was going to ask similar questions, right? So for central projectors, you should have a corresponding more easily stated, because you don't need to worry about DG algebras conjecture.
Mm-hmm.
And I was also going to ask whether you expect a similar thing for gate-square central sheaves.
Yeah. Should
maybe
okay.
To lambda, you'd associate. Just trying to.
So the problem that I don't know is, do central sheaves folks consider what would be infinite complexes as Soergel bimodules? They might only see finite complexes. So instead of PT, you would have these finite.
Yeah.
You'd have like these things that I would call KT, which are.
No, those are just different things. No, gate-square central sheaves are like Schur functors of tautological bundle. So these are very different things. So these are not supported at one point, and these are not like eigenobjects for anything.
I might have misunderstood the question.
I think Ben is asking like, what is the meaning of gate-square central sheaves in this setup?
Yeah, exactly. I was trying to see if if there's some way to extract from this some sort of nice description of what the endomorphism of some gate-square central sheaves should be.
Yeah, I mean, in principle, yes. Like concretely, I don't know, but I mean, you can certainly write some kind of sheaf on all those Hilbert schemes and say, compute derived endomorphisms of this sheaf and hope for the best. And, yeah. But like this description with commuting matrices is specific for projectors, but like in principle, yeah. So for central sheaves, we know what kind of object on the Hilbert scheme you get, and then you just need to compute endomorphism of that object and hope for the best. And in some cases, I think this is not.
Yeah, I wouldn't expect something. I mean, you could wonder, take your Gates-Gorey central sheaf thing, thought of as a complex of Soergel bimodules, and I mean, express it. So apply this decomposition of identity to it. So express it as a twisted complex built from projectors, and then try to compute Homs in this way. But what you get might be kind of horrible, because even if we can compute endomorphism rings of these projectors, we still don't know what Hom spaces between these projectors would be, and those would, I mean, definitely appear.
We can say that these are kind of, so you have like one open chart for one thing, you have another open chart for another T, and then you just look at the intersection of charts, roughly speaking.
Yeah.
But yeah, I mean, we had this long discussions, whatever. Yeah.
But yeah, I don't know. This is.
But in some sense, like this big algebra that is on this page, this governs everything. So this governs like both the endomorphism of individual projectors and the Homs between different projectors. Because these are like, in the end, these are maps between different localizations of the same algebra. Yeah, I guess, I don't know.
I'm still concerned about computing Homs between projectors which are far apart. There's no reason they should be algebras in general.
But they should be bimodal. So you have like localized in alpha and you localize in beta, and you want to compute Homs. So this is, roughly speaking, like localizing both alpha and beta.
But yeah, but the thing you get by localizing in this way will be an algebra. I don't know why the Hom space between two projectors should be an algebra.
I mean, it's a Hom between algebras. I mean, it's not an algebra. Might be more complicated. I don't know.
Yeah.
But I think like it should be true that this is a Hom between localizations. Whatever it is. Anyway.
But aren't there two algebra structures? So one is the algebra of polynomials over a piece in Hilbert or flag Hilbert scheme, but the other is when you start composing Homs, say between projectors. That one, even endomorphisms of a projector, they don't have to be commutative, do they?
They do.
Sorry?
They do, yes.
Oh, they are commutative.
But I would point out that if you have two projectors, okay, this is not. Okay, if you have two like idempotents, I don't know, P and Q, you might guess that the Homs from P to Q should be an algebra because you can tensor P and you can tensor Q. You can tensor morphisms. So if you have a Hom from P to Q and another Hom from P to Q, then
you can put one on top of the other.
Then their tensor product is just a Hom from P squared to Q squared.
Yes.
But P squared is P and Q squared is Q.
Yeah, you're right. Sorry.
However, this tensor product factors through. Such a product is automatically null homotopic because it factors through P tensor Q, which if P and Q are orthogonal idempotents, is contractible. So you would not expect this to be an interesting product in. You would not expect this to be an interesting product on the House space. The totally bizarre thing is, it sometimes is an algebra. But in a weird way. I don't know, like, I just say like, so if you have, for example, in this situation, consider we have two idempotents. And this is a map of degree 1. So the reality is Homs from, goodness, to turn off notifications. Homs from this projector to the identity is an algebra with this guy as playing the role of a unit. Homs from the identity to this guy is an algebra with this guy playing the role of a unit. And Homs relating the projectors is also an algebra with this guy playing the role as a unit. But it's like a degree 1 unit. So the multiplication actually should be thought of as a multiplication of degree -1. So it's a little bit weird. And I'm just, this is the reason why I'm skeptical that if you start computing Homs between projectors, and the algebra structure here is very special. I'm
sorry, what is delta squared?
Delta squared. Delta. It's the identity. Delta squared is the identity. Delta squared is delta.
I'm sorry. But you just said that it would be 0.
Well, delta squared computed like delta tensor product delta would be 0. But delta multiplied with delta in this algebra structure is delta. Like the algebra structure I want to consider here is different from just the usual tensor product. It's something funny. I don't know. I haven't thought about this in quite a while, but you can think of this one as, you can think of the relationship between these three guys as being kind of like the relationship between group homology, group cohomology, no, group cohomology, group homology, and like Tate cohomology. For those of you who like these things. But I've rambled enough. Anyway, so yeah, I mean, yeah. Arms between projectors is so weird, but yeah.
I'm going to take this pause as an opportunity to thank you again. So let's thank Matt for a great talk and question session.
Thank you.
And I'll stop the recording and let Matt choose whether he wants to stay here.